Hi everyone, my name is Xingyu Chen. I'm a fourth-year PhD student from UC San Diego. I will present our research on from bit to token, knowledge-driven generative communication of multimodal data. So for the past few decades, our communication network were designed with humans as the dominant consumers, whether it's a live streaming, video conferencing, or web browsing. The end goal has always been the human perceptual fidelity. But we are now entering a new era for AI. The primary consumer of network bandwidth are no longer humans, but machine-based decision makers. So for example, in autonomous driving, drone control, or industrial robotics, sensors capture the data not for human to watch, but for AI to make decisions and take actions. But the problem is that our current communication infrastructure has not catch up with this shift. Today's wireless networks, such as 5G and Wi-Fi, are built on Shannon's paradigm. They optimize for bit-level fidelity and minimize bit error rate. But many applications do not care about every single bit. They care about the task performance. For example, can I detect the pedestrians, or can I segment the road? So this creates a fundamental mismatch. So when the packets are lost due to channel fading or interference, we usually rely on retransmission to recover the bits, the lost bits. But if you add the latency, so for real-time applications, this kind of latency is not acceptable. So our core research question is, if the transmitter and the receiver are like AI models with some kind of intelligence, do we really need to recover every single bit to understand the semantic meaning? Here we propose the knowledge-driven communication. So the core idea is transmitting the knowledge, not data. So look at this sentence, for example, a quick brown blank jump over the lazy dog. So even though the word is lost, you can still inference and know it is the word fox, because so you don't need to. You do not need the exact bit to understand the meaning, because you already have the knowledge of English and maybe even this common phrase. The intuition motivates our system design. So instead of treating communication as a problem of perfectly reconstructing the raw data, we treat it as a problem of delivering the new information that the receiver actually needs. So if the receiver already has some relevant context, then the transmitter can focus on sending the compact semantic tokens. The receiver can combine those tokens with its own knowledge to recover what matters for the downstream tasks. This is more like a conversation between two humans. So the receiver has some accumulated knowledge. For example, as shown in the figure, the elder lady on the right knows her daughter's voice and what their dog looks like. So the transmitter only needs to send the fresh knowledge. The receiver combines both existing knowledge and fresh knowledge to restore the reality. Here is a high-level architecture. So the transmitter takes a task prompt to generate a task-specific operator using LLMs. Please note this query of LLM is done completely offline, so it only needed once per transmission section. The operator then converts the multimodal sensor data into tokens. And these tokens are transmitted through the lossy wireless channel. on the receiver side, a restoration model retrieves the relevant knowledge from a knowledge base and uses it to get the restoration. The important point is that the communication no longer only between encoder and decoders, it is between the encoder, decoder, the tasks, and accumulated knowledges. So let's look at the transmitter. So our transmitter are designed to handle many types of input: the images, the video, volumetric data, or even point calls. We can use the patch tokenizer from the corresponding foundation models to convert the data into a sequence of tokens. And this lets us to unify different type of sensor data as long as there is a corresponding tokenizer for them. It also allows us to achieve zero-shot task adaptation, as shown in the example on the right. When a task is, for example, the baby monitoring, the transmitter will focus on the bed area where the baby is lying on. And when the task is changed to pet monitoring, the focus will shift to dog. So we do not need to retrain a neural network model for different type of tasks. Because it's a lossy various channel, the receiver gets a token stream that is partially lost. So, but instead of asking for retransmission, the receiver will reconstruct them. The knowledge base retrieved context relevant to the scene, such as the road, the car, the vegetations. That the context is fed through a conditioning layer that modulates the restoration network at every scale. So the network is not generated freely, but it's generating condition on what's already known about the scene. The restored data then flow back into the knowledge base, so the receiver gets smarter as the longer it runs. This creates a positive feedback loop. The high confidence decoded frames are stored in the knowledge base. So the more the receiver sees, the more context it has, and the less data it needs to receive to achieve the desired performance. This also enables a early exit. So when the receiver can where the receiver can stop listening once its confidence is high and can help to save the latency. So a key design goal is to make this system actually practical. So we do not want to replace existing codecs or hardware accelerators. So instead, KDC is a source coding method and works as a wrapper before and after the standard codecs, such as the JPEGs or H.264. The idea is semantic pre-quantization. So for the regions that has less importance to the task, such as the backgrounds, we apply more aggressive quantization to reduce the entropy before the actual standard encoding. The standard codecs then naturally assign fewer bits to those regions while preserving more details in the task critical areas. So the output is still a standard capable bit stream, but it's optimized semantically rather than uniformly. We evaluate KDC across multiple modalities on various protocols. For images and video, we tested over real 5G cellular networks. And we also tested for radar and on a transmission on an indoor Wi-Fi. We also tested for LiDAR, and we used LoRa operating on a USRP device. The goal is to show that this knowledge-driven communication is not a single modality trick, but it should work whenever the receiver can use the task knowledge and accumulate context to recover the information that matters. Here I show some results on the images and the videos, because the image and video are most important and they are harder to transmit efficiently. So radar and LiDAR results are shown to have the similar trends, and those results are included in the paper. On the left side, we show the image and the video transmission under different packet loss rate. As the various channel gets worse, traditional pixel-based codecs degraded very quickly, because missing packets sometimes will corrupt the received images. But in contrast, the KDC is much more robust. So even the packet loss is about 10%. KDC still preserve useful semantic information and achieve roughly 3 times higher task performance. On the right side, we show the transmission under different bandwidth constraints. So our system can keep the task relevant region and reduce the cost of less important region. So it reaches similar accuracy with about half the transmitted bits. So the KDC helps in both difficult channel conditions and tight bandwidth conditions. So when the channel is unreliable, it helps to improve the robustness. And when the bandwidth is limited, it helps improve the efficiency. This is exactly the benefits of moving from bit level reconstruction to task-aware, knowledge-driven communication. And to make KDC practical on real hardware and applications, we need to consider efficiency and latency. We implement the system using a parallel pipeline structure. The KDC's processing, encoding, and transmission runs as a producer-consumer stages. The performed KDC operation are stateless, so they can be parallelized. We also cache important scores for similar frames. So as a result, we can achieve 32 frames per second at 1080p on an edge device, and over 100 frames per second on a laptop with modern GPUs. To conclude, the knowledge-driven communication represents 3 major contributions. First of all, we believe this is kind of a paradigm shift. So using the tokens as the basic transmission unit instead of bits. Second, we provide a system realization of knowledge-driven communication. And lastly, we believe it is a general and practical, as we demonstrated across multiple modalities and protocols with real-time performance. And thank you. That's all for my presentation, and I'm happy to take any questions.